Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, my dear students. Today we are going to start chapter 2 electrochemistry by entering lesson 46 galvanic cell. We should be able to define oxidation, reduction, and redox reaction, sketch and describe the components and operation of a galvanic cell, write half-cell equation, overall cell reaction, cell notation for a galvanic cell, explain electrode potential for a metal immersed in metal solution, and finally define the E-node and E-node cell. In Surah Al-Zalzalah, Zarah is described to be the smallest discrete unit of the universe. Who said atom is the smallest? Democritus said that. This is Democritus. And then Ibn Sina, read what Democritus writes and wrote about this for John Dalton to read. Ibn Sina quote what Allah subhanahu wa ta'ala said in Surah Sabah. The translation is, "But those who disbelieve say, the hour will not come to us. Say, yes, by my Lord, it will surely come to you. Allah is the knower of the unseen. Not absent from Him is an atom's weight within the heavens or within the earth, or what is smaller than that or greater, except that it is in a clear register." This verse is revealing that they are smaller element than atom. Ibn Sina, inspired by the verse, has proven that atom can be split by using mathematical calculation in his book Danish Nama-e-Alai. Later, in 1897, Thomson found electron in his experiment. Now, let's revise what have you learned previously. Let's say we have an atom A and B. A will lose one electron and become A plus, a cation. A is oxidized and A itself is a reducing agent. This arrow is referring to the electron. That particular electron that is released by A is received by B. When B gain electron, it becomes B minus, an anion. So B is reduced and B itself is an oxidizing agent. By transferring electron, an atom will undergo redox reaction and transform into a different physical state of matter. Electrochemistry is the study of how electric current is produced from chemical reaction and also how electricity can create chemical reaction by using reduction and oxidation reaction. So reduction and oxidation cut short, we get redox reaction. Let's look at table 2.1 of our course book. We want to differentiate between reduction and oxidation. Reduction gain electron, but for oxidation process, it lost electron. The simplest way to differentiate between these two processes is by looking at the oxidation number. For reduction, the oxidation number of that atom will decrease, but for oxidation, it will increase. Now, where are these processes happen? They occur for reduction at cathode, for oxidation at anode. So for cathode, we design a simple formula so that we can easily remember where a reduction will occur. Red cat. Reduction happens at cathode. What is red cat in Arabic? Tell me. Qittatun hamra'u. Right? So remember, reduction will always happen at cathode. For example, you can see here the copper ion 2+. The charge is 2+. When it received electron, when it gains electron, it will turn into the solid form. And this solid form has the oxidation number of 0. The oxidation number decreases from 2+ to 0. Right. For oxidation, it happens at anode. We don't have any formula for that. You just do it against the red cat. And the magnesium solid has oxidation number 0. When it releases electron, it will form magnesium ion 2+. So the oxidation number increases from 0 to 2+. So here are the differences between the reduction process and oxidation process. There are two types of cell. The first one is electrochemical cell, or we can also call it galvanic cell or voltaic cell. Why do we call it voltaic cell or galvanic cell? Because chemical reaction produces electricity. The electron produced by the spontaneous redox reaction will go through the wires where it will be detected by galvanometer or voltmeter. So here chemical energy is transformed into electrical energy. The second type of cell is the one that you have done previously at school, electrolytic cell, whereby we will use battery to supply electrical energy and chemical reaction will be produced. Let's look at the diagram of electrochemical cell, galvanic cell, which you, after this, must know how to draw. Okay, firstly, we look at the wires. The wires came out firstly here. So the anode would be on the left, the cathode would be on the right. And then what happened is we are going to draw two beakers side by side. And then, okay, there is an indication of there are solution inside the beaker. And on the left is zinc sulfate aqueous solution, whereby zinc 2+ ion and SO4 2- ions are freely to move within the solution. On the right beaker, we have copper sulfate solution where we have copper 2+ and sulfate ion inside the solution. Now, we are going to dip in the zinc electrode on the left beaker with its zinc sulfate solution, and on the right beaker we are going to have copper electrode dipped into it. Now, this circuit is not yet completed because we have to combine this by putting a voltmeter or a galvanometer, and between the beaker we need to put salt bridge. Okay, let's look at the salt bridge. Yeah, that is the salt bridge. We will see the function of a salt bridge later. And here is your complete circuit of the voltaic cell. The electron will move from anode to cathode, whereby zinc will undergo oxidation, releases electron that will go through the voltmeter. and that particular electron will be gained by Cu2+. Cu, copper electrode, will become heavier, whereas zinc electron will become lighter. Electrochemical reaction consists of reduction and oxidation. Oxidation happens at anode, reduction happens at cathode on the right. These two reactions are called half-cell reactions. When we combine those two, we're going to get overall cell reaction. Example, with the reaction that we have done earlier, zinc solid will release electron and produce zinc ion. That's why I said just now, zinc electron will become lighter, or the mass will decrease. And this particular electron is going to be transferred through the wires and will be received by ion copper, and copper solid will be formed. That's why I said the electrode for copper is going to increase its mass. Combine these two. How do you combine these two half-cell reactions? Cross out the electron on the left and on the right, and you are going to get the overall cell reaction like the ones that we showed you down there. Cu2 plus aqueous plus zinc solid becomes Cu solid plus zinc 2 plus aqueous. Having the electrical current, the electron that moves, between zinc and copper system explain that there are potential difference between the two atoms or system. Potential difference of energy, we called it electromotive force, EMF. Across the circuit, we call it voltage. A voltage is the measurement of the amount of energy, joules per unit charge, coulomb. This is highly physics. The potential difference between zinc and copper can be determined when zinc electrode is dipped into a solution of zinc sulfate, while copper electrode is dipped into a solution of copper sulfate. The solutions, called half cell, are connected with an external circuit, salt bridge, so that zinc can transfer its electrons to the copper ions. So soon we will look at how the ions in the salt bridge helps completing the circuit. There's more explanation here. The combination of two cells is called a galvanic cell. And the potential difference in the zinc-copper system is 1.1 volts if both solutions have a concentration of 1 molar each. This process is involved describing electrochemical changes, and this kind of study is called electrochemistry. Now, what is salt bridge? Salt bridge is an inverted U-tube. It contains a gel permeated with solution of an inert electrolyte such as potassium chloride, sodium sulfate, or ammonium nitrate. Our U-tube in the lab is made by Sir Faris himself. So be careful when you are touching them. Do not ever put it barely on the bench. What are the functions of salt bridge? Number one, it helps maintain electrical neutrality. Number two, it completes the circuit by allowing ions carrying charge to move from one half cell to the other half cell. Let's look at what happened to the cell if there are no salt bridge. So we construct the same cell with zinc and copper in each beaker, and then the electron will move, but the second electron is stuck because the neutrality in the beaker is not balanced. As the zinc rod dissolves, the concentration of zinc 2 plus in the left beaker increases. The reaction stops because the net increase in positive charge is not neutralized. How does the cell maintain its electrical neutrality? Let's look at the left cell. What happened is zinc solid releases electrons, and zinc 2 plus ions produced will enter the solution. It will cause an overall excess of positive charge. If we have salt bridge, Cl- from the salt bridge will move into the zinc half cell beaker, and the neutrality is balanced. In the right cell, what happened is copper 2 plus ion will receive the 2 electrons and produces solid copper. But when copper 2 plus ion leave the solution, it will cause an overall excess of negative charge. What happened is the potassium ion from salt bridge will move into the copper half cell. This will help maintaining the electrical neutrality, and the process can go on and on. Let's look at this diagram of the same cell. We close up to the zinc electron. Can you see here the zinc solid releases electron, and the electron goes up, wanting to go through the wire, and then what is released is the zinc ion. Here it says zinc is oxidized to zinc 2 plus at anode, and the half cell equation is given. At the copper electrode, you can see here it is zoomed in. The electron from the wires come down and received by the copper ion, and it will become copper solid. Copper 2 plus is reduced to copper solid at cathode, and the half cell reaction is given down here. The net reaction or the overall cell reaction is given here. So you can see there this reaction is called spontaneous redox reaction. On the left is the anode where oxidation occurs, and on the right is cathode where the reduction occurs. The next part of the lesson is for us to know what is cell notation. Cell notation is a simplified equation. Chemists create equation to make reaction simplified, but electrochemists simplified the equation into cell notation to simplify everything. So let's look at the first cell notation for you using the same galvanic cell we have done previously. The left part of the cell notation would be the anode part, whereby zinc solid on the left, separated by this line, vertical line, and this one is the product. Zinc solid becomes zinc ion in aqueous form. So this part is the anode part in the beaker. What about the right part? The right part is the reactant, copper ion, aqueous, becomes copper solid, separated by a vertical line. In between the beaker, in between the anode and cathode, we have two vertical lines representing the salt bridge. So the half cell for reduction is at cathode on the right, and the half cell for oxidation is at anode on the left. So this is figure 2.3 cell notation of the zinc copper cell. Okay, let's repeat the explanation. Anode is placed on the left side, cathode is on the right side. Single vertical line is to represent the boundary between different phases, such as between an electrode and a solution, between a solid and an aqueous. Double line is to represent a salt bridge separating two half cells. In each half cell, the reactants are written first, followed by the products. For half cells that do not have any metal that can function as an electrode, an inert electrode, whether it is carbon or platinum, is used. An example, this is a different example. Zinc solid react with 2 ferrum 3+ ion aqueous becomes zinc 2+ aqueous and 2 ferrum 2+ aqueous. So here, as you can see, the reactant for ferrum is both liquid, same as the product, it's both liquid. So what is the cell notation? As we can see here, we put zinc solid on the left side of this vertical line because it is being oxidized to become zinc 2+. So this is a different phase, so we put a slash or the vertical line. And then this is the salt bridge. Right. For ferrum, 2+ and 3+ both is aqueous, so we cannot put the vertical line. Instead, we put comma. The vertical line would be at the far right, whereby we need to use a platinum solid to replace the function of the electrode. Let's do example 2.1. The following spontaneous reaction occurs when metallic zinc is dipped into a solution of silver nitrate. Given the overall cell reaction, what is the reaction in each half cell? You can derive that from the overall cell reaction. Write the cell notation and then sketch the diagram of the cell and label the cathode and anode and the charges in each electrode, the direction of the ion and the electron flow. Indicate the positive and negative electrons. So there are so many things that you have to do. Let's do it together one by one. So this is the answer. For oxidation, zinc solid will release its electron to form zinc 2+ ion aqueous. For reduction, Ag+ aqueous will receive 1 electron to produce argentum solid. Down here is the cell notation. You can see that the oxidation part is for zinc solid and zinc ion. It is separated by a vertical line here because the state phase is different. This is the salt bridge, and then at the reduction part, the cathode, you can see Ag+ aqueous receive electron and it will become argentum solid. This is a sketch of the diagram that you have to draw. Please use your skills not to depend on the ruler much, because you need to do it quick. So Quickly draw the beaker, quickly draw the electrode, the salt bridge and the electron flow, and you have to do the thinking on the electrode and the solution, which will be on the left and which will be on the right. That one is more critical than using the ruler. Sometimes I see students put a lot of effort on things that does not need brain. Okay, so you put zinc electrode dipped into zinc nitrate on the left side of the beaker, and you can see the electron flow is going up here. It is labeled here electron flow. So electron will go down to the right side, and here at the reduction part, the cathode is argentum solid and the solution is argentum nitrate. As you can see, the salt bridge used is filled with the solution of potassium chloride, and this is the arrow where the ions will flow. The K plus potassium ion will flow into the right beaker, and the anion Cl minus will flow into the left beaker. So these are the arrows, the labels that you need to have in order to get at least 5 marks. That's a lot. This is a practice that you have to do on your own. Please do it first before watching the explanation or asking me about it. You need to write the half cell equations from the overall cell above, and then write the cell diagram and draw a sketch of the cell by labeling all the things that we have done previously. For question number 2, you have to construct a cell diagram. So you have to be careful to look at the face. If the face is different, then you can use the vertical line. But if the face is both in aqueous form, you need to choose an electrode, carbon or platinum, and put it at the back far end, whether it's on the left or it's on the right. That is for you to determine. The next part of the lesson is to calculate the cell potential and the standard reduction potential. We know that for different metals, it has a different potential energy. I believe you already memorized the ECS table, Electrochemical Series table. The potential difference between the two metals acts as a driving force or electrical pressure that pushes the electrons through the wire. It's a spontaneous reaction. So electromotive force, EMF, is the maximum potential difference across a cell. Electrode potential is a measure of the half cell to attract electrons in unit volt. It can be positive, it can be negative. If it is positive, the reaction is spontaneous, but if it's negative, it cannot occur. Standard electron potential refer to reduction half cell reaction. So we name them standard reduction potential E0 rad. Cell potential E cell is the sum of electrode potentials of the two half cells making up the electrochemical cell. Standard conditions is referring to the conditions whereby the temperature is 25 degrees Celsius, the pressure is 180 M, and the concentration of the ions involved is 1 molar. The standard cell potential E0 cell is calculated using the relationship E0 cell equals to E0 rad plus E0 ox. Rad stands for reduction, ox stands for oxidation. Or E0 cell equals to E0 cathode minus E0 anode. We can use both formula. I will show you how. Let's do example 2.2. From the standard reduction potential table, this is in your course book. Given half cell equations below, calculate the E0 cell. Look at the E naught red. This 2 is E naught red. You see? Because both of the equation is a reduction reaction. We have to know which one is going to be oxidized in order to calculate the E naught cell. So how are we going to use the formula? Firstly, we need to know which element which is going to be oxidized. So we need to look at the E naught red. The E naught red which is higher is going to become the oxidizing agent, and it is going to be reduced. So what is it going to be oxidized? The one that has lower E naught red. So the one that has the lower E naught red is zinc, negative 0.76. So when it is oxidized, the sign changes into positive. And we add together with the E naught red of copper. The answer is 1.1 volt. The first formula, we have to change the sign for oxidation. But for the second formula, the E naught N naught must be used straight away from the table, negative 0.76. But since it is a minus sign, it is deducted from cathode, so it becomes positive. 0.34 plus 0.76 here. So the answer is the same, 1.1 volt, whether you use the first formula or the second formula. For practice 2.2, nickel and stannum. In between these two elements, which one is going to be oxidized? Which one is going to be the anode? The ones that has the lowest E naught red, nickel. After that, you are able to calculate the E naught cell. For question number 2, an electrochemical cell consists of a left compartment with zinc electrode, 1 molar, zinc nitrate, and right compartment with silver electrode, 1 molar argentum nitrate. The standard reduction potentials are given below. For this question, it already tells you the left compartment is zinc. So it is an anode. Therefore, zinc will be oxidized. Positive 0.76 is the E naught ox. So you can calculate the E naught cell easily after this. Thank you very much for watching. I know as the first lesson of electrochemistry, it's a bit too much, but please bear with me. Galvanic cell is very important and you need to understand it now. Assalamualaikum warahmatullahi wabarakatuh, and stay tuned. I will see you again soon. Bye.